when you have a mass on a spring in harmonic motion, energy is going to be conserved because this is frictionless, and the only force acting on it in the horizontal is the spring, okay? And so energy is conserved. So spring energy is considered a conservative force. Yeah, does the spring do work on it? Remember, for you AP folks, it does work if your system is consisted only of the mass itself. But when we're talking about energy conservation, we talk about the energy of elastic potential energy of a spring, okay? And your system becomes the object here, the spring itself, and the earth, but we're just doing a horizontal system. And all of your springs will have negligible masses, right? A light spring. So, the energy at any given point, I'm just going to use an A and a B, is equal to a constant. Well, what is the energy made up of? You've got the kinetic energy plus the potential, and it's spring energy, all right, elastic potential. And that equals a constant, wherever it is. What is this? This is 1/2 times the mass times the velocity of the object at that point in its motion squared, plus 1/2 kx squared. Okay, be sure that this is in kilograms, meters per second, newtons per meter, meters. All right, the units matter. And that equals a constant. Now, at any given point, that's how you can relate the position to the speed for a spring. Okay, its position and speed are related by this. Well, let's write this equation for when it's at amplitude. Well, if it's at amplitude, so at amplitude, at maximum amplitude, at A, you know that V equals 0. So what does this look like at amplitude? It's going to be 0 because there's no velocity at amplitude, plus 1/2 kA squared. That's a constant. What about when it passes to equilibrium? Let's do that in purple. At equilibrium, at that, x is equal to 0, and v is your maximum. And that's how you find the maximum speed of an oscillating mass on a horizontal spring, actually in any situation, is when it passes through equilibrium. All right, it maximizes its speed at equilibrium. And so in that case, this is 1/2 mv max squared plus 0, because x is 0 at equilibrium, equals a constant. So you have that equation there when it's at amplitude. You have this equation when it's through equilibrium. And then you have this equation at any other time. All right, at any other point other than equilibrium. And remember, they all equal each other. So that equals that at amplitude equals that at equilibrium. So depending on the situation that you're given, you set up the energy equation and then solve for the unknown variable. So just generically, you have 1/2 mv squared plus kx squared. That's your, at any position, equals 1/2 kA squared when it's at amplitude. Notice that these are squared, and so that whether it's to the right or to the left doesn't matter because you square the negative sign, becomes positive. That's at amplitude, and this is at equilibrium. All right, at equilibrium. Notice also that the halves cancel. Whoopsies, bad teacher. There's a half in here. You may not be able to see it, but it's there. All right, it's a 1/2 kx squared. A 1/2 kx squared. you have the haves and the have-nots. Sorry, that's a bad joke. And now you can rewrite that, and you use whichever you use, depending on what you're looking for, what you know, right? So mv squared plus kx squared equals ka squared plus m v max squared. And no, whoops, it's an equal sign. Golly. Equals and equals. And no, nothing cancels any more than after the halves, all right? So don't go canceling the k's and the m's or any of that stuff. Again, this is anywhere. This is specifically the energy at amplitude. Well, it's half. It'd be half of that, right? And then this is specifically at equilibrium. Well, what do you do with that? Well, if you're solving for the maximum speed and you know the amplitude, solve for that and take the square root. If you're solving for the amplitude and you happen to know the maximum speed, solve for that. If you know, for example, the amplitude, you want to figure out its velocity at some position. Let's just do that, for example. Let's say that you know the amplitude. So mv squared plus kx squared equals ka squared. And you want to know how fast it's going, or this is speed, not velocity, how fast it's going at a certain position, given the amplitude and the value of k. Well, solve that thing for v. So I'd subtract that to the other side. So mv squared equals k, and that's going to be a squared minus x squared, because I subtracted that over there, a squared minus x squared. And no, you can't just go take the square root of that as it is, and it's not going to simplify it if you did. And I'm going to divide through by m, and so v squared equals k over m, a squared minus x squared. And so v equals the square root, and it's actually plus or minus because it could be to the left or to the right. Am I running out of room here? No, I'm all right. Of k over m times a squared minus x squared. All right. One more thing to write. What's the square root of k over m? The square root of k over m is omega, all right, angular frequency. So the velocity at any given position is that. If you know k over m, just leave it like that. If you happen to know the angular frequency, then it's plus or minus the angular frequency times the square root of a squared minus x squared. All right. I would not memorize this. This is what you need to know. All right. The energy is conserved. It's a constant. What is the energy? It's kinetic and potential energy. Okay. You should be able to derive this each time. Absolutely should be able to derive this each time. Don't waste your time memorizing these equations. It's not going to help you in the long run. Okay.